There's a star in our galaxy that doesn't behave like any of the others. It doesn't shine the brightest or burn the hottest, or even sit quietly in some familiar corner of the night sky. Instead, it spins so fast it puts jet engines to shame, and it's so dense that a single teaspoon of its material would outweigh a mountain. But that's not even the scary part. The real problem is that this thing is unstable. It's on the edge. One wrong move, just a little more mass, a little more pressure, and it collapses into something even worse, a black hole. And the thing is, this isn't some distant object on the edge of the observable universe. It's in our galaxy, right now, spinning, feeding, growing. Scientists have known about it for a while. They even gave it a name. But for all the data we've gathered, there's still one question they can't answer. When is it going to blow? Or maybe the better question is, are we sure it hasn't already? When a massive star reaches the end of its life, it doesn't go quietly. It burns everything it has trying to fight off the inevitable, gravity. And once its nuclear fuel runs out, gravity wins. The core collapses, the outer layers explode in a supernova, and what's left behind is something strange, something small, something impossibly heavy. What you get is a neutron star. It's not just dead, it's transformed. Now, a typical neutron star isn't much bigger than a city, maybe 20 kilometers across. You could drive across it in under half an hour if you could somehow land on it without being crushed or vaporized. But in that tiny space, it holds more mass than our sun. That's like taking every person, planet, mountain, and ocean in our solar system and stuffing it into a sphere the size of Manhattan. Here's where things get wild. Because it's so compact, a neutron star has insane density. 1 teaspoon of this stuff would weigh over 1 billion tons. That's more than the weight of every building in New York City, combined. If you dropped a piece the size of a sugar cube onto Earth, it wouldn't just sit there. It would punch straight through the crust, tear through the mantle, and keep going until it hit the core. It wouldn't even slow down. But that's just the beginning. Some neutron stars spin, not just slowly rotating like Earth. They spin fast, so fast that they flash beams of radiation across space, like the rotating light on a lighthouse. That's what we call a pulsar. Not because it pulses like a heartbeat, but because those beams sweep past us at regular intervals. And they look like pulses when we detect them. At first, scientists had no idea what they were. Back in 1967, when Jocelyn Bell Burnell first picked up the rhythmic signals of the first known pulsar, the team didn't rule out aliens. That's how strange it was. Something in deep space was sending radio pulses with the timing of an atomic clock. Later we figured it out. It wasn't ET. It was something much weirder. These things spin at hundreds of revolutions per second. That's faster than the blades of a helicopter, faster than your kitchen blender, and in some cases, even faster than a jet turbine. They're cosmic flywheels that dwarf human-made machinery in both speed and endurance. And they don't slow down easily. Many of them have been spinning like this for millions of years. Pulsars maintain these speeds for millions of years due to their immense angular momentum and low energy loss. And here's where it gets dangerous. Some pulsars don't just exist alone in the void. They find companions, not by choice but by force, through a process called accretion. This process can keep them spinning rapidly for extremely long periods. Nearby stars are caught in their gravitational grip. Over time, the pulsar gathers enough material from these unfortunate companions. The doomed companion, often a low-mass star, is stripped of its outer layers, its matter torn away in a searing stream of superheated plasma. This spiraling torrent of gas funnels into the pulsar, delivering a surge of energy. It spins faster, it gains mass, it becomes more extreme. Scientists call these black widow pulsars. Just like the spider, they consume their mate after mating. Only in this case, the pulsar doesn't just kill its companion, it eats it, atom by atom. This process doesn't go on forever. There's a limit to how much mass a neutron star can hold, and once it gets too close to that line, the structure can't hold anymore. The neutron pressure fails, gravity takes over, and the pulsar collapses again, this time into a black hole. So when we say some of these stars are dangerous, it's not because they're going to explode and send shockwaves across the galaxy like a supernova. It's because they're already past the point of being ordinary stars. They're dense, powerful, spinning time bombs. And the one we're focusing on isn't just any pulsar. It's the fastest spinning, heaviest neutron star ever discovered. And it's sitting right here in our own galactic neighborhood. Let me show you what makes this one different. Not all pulsars are equal. Most of them spin fast, yes. Most of them are dense and powerful. But every once in a while, astronomers find something that doesn't just fit the definition, it redefines it. One of those is called PSR J0952-0607. It doesn't have a flashy nickname and it's not in a sci-fi movie. But what it does have is a resume that reads like a warning label from the universe itself. This thing spins at 707 revolutions per second. That's not a typo. Every second, it completes over 700 full rotations. You couldn't even blink that fast if you tried. It's so fast that its surface is moving at a significant fraction of the speed of light. And yet it's not flying apart. Gravity holds it together, squeezing it so tightly that even atoms themselves don't exist on the surface anymore. The only thing left is neutron matter, crushed so hard that electrons and protons have merged. And as if that wasn't enough, it's also the heaviest neutron star ever discovered. Nearly 2.4 times the mass of the Sun, all crammed into a space just 20 kilometers wide. That combination, extreme spin and near critical mass, is why this object is dangerous. Because here's the catch. Neutron stars aren't supposed to weigh that much. The upper limit, the so-called Tolman-Oppenheimer-Volkoff limit, is estimated to be somewhere around 2.5 to 3 solar masses. Beyond that, the neutron pressure can't resist gravity anymore. The star collapses into a black hole. So this one, it's close, really close. And we now know how it got this way. It wasn't born this massive, it ate its way here. Orbiting this pulsar is the dim, fading remnant of a star, a white dwarf that's being slowly ripped apart. Like a drop of water falling into a drain, its matter spirals toward the pulsar. Some of it falls in. Some of it forms a hot, glowing accretion disk. Either way, the pulsar gains mass. It also gains spin. Just like an ice skater, pulling in their arms, shrinking the radius increases the angular momentum, and the more it feeds, the faster it spins. That's what makes these kinds of systems so extreme. The process doesn't just accelerate the pulsar, it puts it under pressure. Every gram of stolen matter is one step closer to the breaking point, one step closer to collapsing. Astronomers call it a black widow pulsar, and the analogy fits. The pulsar drains its partner until nothing remains. The white dwarf fades, the pulsar grows, and eventually there's nothing left but one unstable, overfed neutron star, waiting for a final push. And here's where it gets unsettling. Unlike a supernova, which announces itself with a visible explosion, this collapse wouldn't give us much warning. There'd be no flash of light, no giant shockwave, just a sudden silence. The pulses stop, and in that silence, a black hole is born. We don't know when that will happen. Could be 1,000,000 years from now, could be tomorrow, could already have happened, and we're just waiting for the news to travel about 14,000 light years to reach us. And just so we're clear, this object is inside our own galaxy. It's not some distant curiosity in a faraway cluster. This is a ticking time bomb spinning at full throttle right here in the Milky Way. And the only reason it hasn't turned into a black hole yet is because it's still holding itself together by sheer momentum. The spin is buying it time. But eventually, time runs out. So, let's say it happens. Let's say this pulsar finally crosses that invisible line. It pulls in just enough mass from its dying companion, and the delicate balance holding it together breaks. What exactly happens next? Well, the star doesn't explode. Not in the way we're used to thinking about explosions. It collapses. Silently. Instantly. One moment it's a pulsar, spinning, beaming, pulsing like a galactic lighthouse. And the next it's gone. The pulses stop. The light vanishes. The radio waves we've been picking up from Earth just cut off. No sound, no flash, just a flick of a switch, and what's left behind is a black hole. This is where the real physics kicks in. Unlike a supernova, which throws off most of the star's mass in a burst of light and gas, a pulsar collapsing into a black hole doesn't leave behind anything visible. There's no outer shell to eject. The material is already compacted as far as it can go, so the collapse is clean. Director, efficient. The mass is still there, but now it's hidden behind an event horizon. The gravitational pull becomes so strong that even light can't escape. From the outside, the object becomes invisible, but its presence is still felt. Space around it warps, time slows near it, and anything too close falls in. Here's the good news. Even if this happened tomorrow, we wouldn't feel a thing here on Earth. At least not for a while. This pulsar is about 14,000 light years away. So, if it collapsed today, the effects wouldn't reach us for another 14,000 years. Technically, it might have already collapsed. We're still seeing the version of it that existed 14 millennia ago. The light we detect, the pulses we measure, are delayed snapshots from the past. But let's say, for the sake of curiosity, that it did collapse. What does that mean for the surrounding region of space? This is where things get uncomfortable. When a pulsar collapses into a black hole, it loses the structure that was keeping its radiation beams aligned. The regular pulse ends, but its environment doesn't instantly calm down. The accretion disk, all that material still spiraling in, keeps feeding it. But now it's not feeding a pulsar. It's feeding a newborn black hole. This can briefly create something called a relativistic jet, an ultra-energetic beam of particles and radiation shooting out from the poles of the black hole, accelerated to near light speed by magnetic fields and rotational energy. If those jets happen to point anywhere near our direction, even from 14,000 light years away, they could do real damage. That's not speculation, it's happened before. Astronomers, including Adrian L. Melott and Brian C. Thomas, suspect that a mass extinction event around 440 million years ago, the late Ordovician extinction, might have been caused by a gamma-ray burst from a nearby neutron star or black hole. It wouldn't have hit Earth like a bomb. Instead, it would have silently fried our ozone layer, leaving the surface exposed to UV radiation from the sun. The result: global collapse of ecosystems, especially marine life. Again, that's rare. Unbelievably rare. And the odds of this pulsar's beam being aligned with us is even lower. Most of the time, these jets shoot off in random directions, and the vastness of space is usually enough to keep us out of the line of fire. Still, the point is, it can happen. And that's why scientists keep watching. But let's flip the question now. What if it didn't collapse all at once? What if it kept growing slowly, pulling in more mass, increasing pressure, getting closer and closer to that critical point, while still spinning at 707 times per second? At some point it reaches a stage where even the spin can't save it. And then, in the blink of an eye, the entire structure gives way. Some models suggest this could unleash an extremely fast, short-lived burst of gravitational waves, ripples in space-time itself. Detectors like LIGO and Virgo might catch it, giving us a real-time signature of a pulsar collapsing into a black hole. That would be a scientific first, but it would also be a cosmic testament. A signal that one of the fastest, densest, most extreme stars in the galaxy just died a second death. Quietly, without warning. And what replaces it? An invisible void. A gravity well from which no light can escape. The beam that once pulsed across the galaxy like a clock, gone. From a cosmic perspective, that's the end of the story. But from ours, it's just getting started. Because there's another kind of neutron star that doesn't wait for collapse to be dangerous. One that doesn't need to spin at 700 times per second to cause havoc. It's not faster, it's not heavier, it's just magnetic. You'd think that a star spinning hundreds of times per second, weighing more than our sun, and teetering on the edge of collapse would be the worst case scenario. But nature, as always, has a way of going further. Because there's another kind of neutron star out there. It doesn't spin as fast. It doesn't have to. It doesn't need a companion star to devour. It doesn't rely on beams of radiation to make its presence known. Instead, it warps the very structure of matter with something far more silent and far more terrifying. It's called a magnetar. Now, take everything we know about neutron stars. The density, the gravity, the compactness, and add a magnetic field so intense that it can literally tear atoms apart. Not just ionize them like regular radiation does. Not just heat them up, it rips apart the structure of matter itself. A typical pulsar already has a magnetic field trillions of times stronger than Earth's. But magnetars crank that number up so high that it stops being relatable. The field of a magnetar can be over 1,000 trillion times stronger than Earth's. If you were anywhere near one, even thousands of kilometers away, your atoms wouldn't hold together. The very chemistry of your body would fall apart under the magnetic pressure. And it's not just theoretical. We've observed their effects. In 2004, a magnetar named SGR 1806-20, located about 42,000 light-years away from Earth in the constellation Sagittarius, released a burst of gamma radiation so intense that it caused sensors on multiple satellites to overload, even though it came from the other side of the galaxy. For a fraction of a second, that magnetar outshone every other X-ray source in the sky combined. If it had been just 10 light-years closer, Earth would have been in trouble. And this is where things get uncomfortable. Because, unlike pulsars, which spin and fade gradually over time, magnetars are unstable. Their magnetic fields don't stay quiet. They build up tension beneath the crust. And sometimes, the pressure becomes too much. This causes what's called a starquake. Imagine a planet-sized object made of ultra-dense neutron matter cracking open, like an egg under too much pressure. The crust shifts. The magnetic field suddenly realigns. And the resulting release of energy is so massive, it makes our most powerful nuclear weapons look like firecrackers. These quakes unleash bursts of gamma and X-ray radiation that travel across space at the speed of light. And there's no warning, no build-up, just a sudden flash. And the energy of 100,000 suns released in a fraction of a second. We're lucky, by the way. The closest known magnetar is about 8,000 light-years away. That's far enough that even a massive flare wouldn't do much damage to Earth. But scientists have calculated that if one went off within about 40 light-years, it could strip away our ozone layer, exposing the planet to deadly ultraviolet radiation from the sun. And here's the kicker. Magnetars don't live long. Their intense magnetic fields decay quickly, over just 10,000 to 100,000 years, which is a blink of an eye in cosmic terms. That makes them rare. For every 1,000 neutron stars, only about 10 are expected to be magnetars. But that's still enough. One is enough. The magnetic field is so powerful that even when the magnetar is quiet, it's still affecting its surroundings. Any nearby planets, assuming they even exist, would be constantly bathed in high-energy radiation. And if a flare did happen while a planet was close, the result would be instant sterilization. You don't need a supernova. You don't need a black hole. You just need a crack in the crust. And it's game over. That's what makes magnetars a different kind of danger. They don't announce themselves with pulses. They don't get louder over time. They're like cosmic mines, sitting in place, quiet, waiting. And if the conditions line up just right, they detonate. So we've got neutron stars that spin fast enough to create artificial light beacons. we've got magnetars that hold the record for strongest magnetic fields in the known universe. And we've got at least one pulsar in our own galaxy that's balancing on the edge of collapse. But let's ask the next logical question. What if one of them was closer? What if somehow one of these stars drifted into our neighborhood? So far, everything we've talked about has felt distant. 20,000 light years, 50,000 light years, even the nearest magnetars are thousands of light years away, comfortably tucked away behind an ocean of space. And that's probably why most people don't feel the weight of it. Cosmic danger, when far enough, doesn't feel real. But let's bring it closer. Let's say one of these neutron stars, doesn't matter if it's a pulsar, a black widow, or a full-blown magnetar, somehow got kicked in our direction. Maybe from a supernova explosion, maybe a gravitational nudge from another star. Space is chaotic, and neutron stars have been known to move. In fact, some of them are moving at speeds of over 1,500 kilometers per second. Fast enough to leave the galaxy entirely. Now imagine one of those stars, maybe even PSR J0952-0607, somehow found itself within the orbit of Jupiter. Let's say it parked itself about 500 million miles from Earth. That's still far, right? Jupiter's out there, no big deal? Think again. First, the gravity. Even from that distance, the gravitational pull of a neutron star that massive would start disrupting the orbits of nearby planets. Jupiter, Saturn, and even Uranus might experience orbital shifts. Over time, their paths would destabilize, creating gravitational chaos that trickles inward, toward Earth. Then comes the radiation. A pulsar like J0952-0607 doesn't just sit quietly. It emits twin beams of high-energy radiation from its magnetic poles. Beams made of X-rays, gamma rays, and charged particles. If Earth happened to be in the path of even one of those beams, we'd be in serious trouble. Our magnetic field would offer some protection for a while, but the intensity would overwhelm it eventually. The ozone layer would be the first to go. Without it, solar ultraviolet radiation would begin sterilizing the surface. And it wouldn't stop there. The constant exposure to high-energy particles would start breaking molecular bonds in the atmosphere. Satellites would malfunction, GPS would be lost, radio communications would collapse, the night sky would be flooded with unnatural light, and the auroras, those dancing green lights near the poles, would spread across the entire planet, flickering non-stop like a warning. And if it's a magnetar instead of a pulsar, well, the rules change. A magnetar doesn't need to spin at 700 times per second to cause chaos. All it needs is proximity. If it were within just a few thousand kilometers, the sheer strength of its magnetic field would start pulling at the electrons in the atoms that make up your body. You wouldn't even see it coming. Your body's structure would simply dissolve, not from heat, not from radiation, just raw magnetic force. And even if you were watching from a distance, say from the moon, the view wouldn't be much better. The Earth would start to deform, not all at once, but slowly. Tides would go wild, the crust might shift. Volcanoes would awaken from dormancy as the pressure underneath builds. Earthquakes would ripple through continents as the gravitational stresses mount. Eventually, the atmosphere itself could be stripped away, blown into space by radiation pressure and magnetic interference. The oceans would boil, then evaporate. The surface would be scorched. Life would vanish, not in centuries or decades, but in hours. And yet, for the neutron star, none of this would be noticeable. To a pulsar or a magnetar, Earth is just another rock, a piece of space debris that happened to get too close. Our sun? Barely a snack. If the neutron star had enough mass, or if it kept pulling matter in through an accretion disk, it could eventually collapse into a black hole right there in our solar system. At that point, gravity would dominate completely. Planetary orbits would collapse inward. The sun itself would spiral toward the event horizon and vanish. And that's the end of the story. Now, obviously, the odds of this happening are extremely low. Neutron stars are fast, yes, and powerful, but space is vast. Most of them are traveling through the galaxy in isolation, and even though a few 100 million exist in the Milky Way, the chances of one wandering into our backyard are lower than winning the lottery every day for the next century. But that's not really the point. The point is, these objects exist. They're real, and they're not rare. They're scattered all across the galaxy, some spinning faster than any human-made machine, some glowing with invisible beams of deadly radiation, some with magnetic fields strong enough to destroy planets without ever touching them. And some of them somehow have planets of their own. After everything we've said about neutron stars, the gravity, the radiation, the magnetic fields that could tear atoms apart, it would be fair to assume that nothing could survive near them. Certainly not something as fragile as a planet, and yet a few have. Not many. In fact, only about 0.5% of all known pulsars have been found to host planets. That's out of the thousands we've detected. But those rare exceptions raise a strange question. How can a planetary system survive around one of the most violent objects in the galaxy? Let's start with the basics. Most stars form planets from leftover material, the gas and dust swirling around them during their early life. But pulsars are formed in the exact opposite way, from destruction. A massive supernova explosion wipes everything out, and what's left behind is a crushed core spinning like a blender with a magnetic field that could sterilize entire solar systems. So, the original planets? Gone. Which means that if a pulsar has planets, they either formed after the supernova, or they were somehow captured later. One of the most well-known examples is PSR J0952-0607, located about 2,300 light-years away. It was the first pulsar ever found to host planets. And believe it or not, it was also the first confirmed discovery of any exoplanets at all, back in 1992. This pulsar has 3 known planets, all of them rocky, all of them bigger than Earth. And what's strange is that they orbit in relatively stable paths. Not normal, circular orbits like we see in our solar system, but highly elliptical, meaning they swing close and then far away as they loop around. The gravitational environment around a pulsar is so intense that even small deviations become amplified. So the fact that these planets are still there and still orbiting is weird. Now imagine living on one. This wouldn't be like Earth. The skies wouldn't have sunlight or a blue atmosphere. They'd be black, permanently. Your sky would flash regularly with bursts of radiation, depending on whether the pulsar's beam crossed your location. Instead of sunlight warming the planet, you'd get occasional pulses of high-energy particles, enough to sterilize any exposed surface. The only chance for life to exist would be deep underground, shielded by miles of rock, maybe under thick ice, maybe in subsurface oceans. Some scientists think these planets might be formed from supernova debris, material that didn't escape into space, but fell back inward and eventually cooled into a dusty disk. Over millions of years, that material could have clumped together into rocky worlds. Others think the planets might be fragments, pieces of a companion star that was shredded by the pulsar's gravity, like cosmic leftovers, compressed into orbit. There's also the possibility that these planets were captured, rogue planets drifting through space, caught by the pulsar's intense gravitational pull. This is less likely, but not impossible, especially if the pulsar once had a companion star that got ripped apart and left behind planetary debris. Regardless of how they formed, these planets are survivors. They've withstood radiation, magnetic storms, and gravitational chaos. And they still orbit quietly around one of the most dangerous objects in existence. Another pulsar, PSR J0952-0607, has at least 2 known planets, again both several times more massive than Earth. One completes an orbit every 1.9 years. The other takes 3.6. And just like with B1257 plus 12, Their paths aren't smooth or gentle. They're elongated, chaotic, and constantly shifting, like a car trying to drive in a hurricane. The weirdest part is that we don't know how rare this really is. We've only detected pulsar planets around a handful of neutron stars, but that might just be because they're hard to see. After all, we're trying to spot tiny worlds orbiting objects that are barely the size of a city across thousands of light years of space. And yet, they're out there. If life ever did evolve on one of these worlds, it would have to be unlike anything we can imagine. It wouldn't just have to survive harsh conditions. It would have to be built for radiation, for chaos, for sudden bursts of energy that could melt an atmosphere in minutes. Which brings us back to Earth. We orbit a calm, steady yellow star. We have a mild magnetic field, a breathable atmosphere, liquid water on the surface. In every possible way, our solar system is unusually quiet. The fact that neutron stars can even have planets just makes it clearer how strange and lucky our situation really is. But let's circle back now, because this whole story started with a title. The most dangerous star in our galaxy might explode any minute. And the question was simple. Should we be worried? So, should we be worried? We've talked about stars that spin faster than jet engines, crush matter tighter than atomic nuclei, and shoot beams of radiation that could melt the surface of a planet. We've looked at pulsars that are eating their companions alive, and magnetars that could crack open like lightning-filled eggs and blast radiation across light years. It sounds like a horror movie, but here's the truth. No, we don't need to worry. Not in the way people usually think about danger. PSR J0952-0607 isn't about to collapse into a black hole tomorrow and erase us from existence. Magnetars aren't hovering nearby, ready to fry our atmosphere. These things are real, but they're also far. That's what saves us. Space, as it turns out, is still very, very big. The most dangerous star in our galaxy might explode, yes, but that any minute, in cosmic terms, could mean tens of thousands of years, or longer. And if something like that did happen, the radiation would take just as long to reach us. So even if the collapse already happened, we wouldn't know. We'd be staring into the past, like we always are when we look at stars. But that doesn't mean these things are irrelevant. Pulsars, neutron stars, and magnetars aren't just freak objects floating in the void. They're reminders that the universe doesn't run on comfort. It runs on physics, on pressure and collapse, on spin and radiation, on gravity, pulling things inward until they can't hold their shape anymore. These stars show us what happens when things are pushed to their absolute limit and beyond. They tell a story that's less about threat and more about scale, because what we call normal, a calm star, a stable orbit, an atmosphere that protects us,